So this means the vector's magnitude. 2 lines here and 2 lines there. That all that means is the length of the vector, the magnitude. And we do that by taking the square root of this side plus this side. Doesn't matter which one's first. I'll do the 2's, Q2 minus P2, and then the x's. Q1 minus P1. Oops. Alright, so this is using the Pythagorean theorem, we get the magnitude. Alright, so theory. Another definition, if the magnitude of a vector, remember the double lines mean the length or the magnitude of the vector is 0, then we call it the 0 vector. Wasn't that creative? And if we have the length of a vector equals 1, we call it the unit vector. So we really outdid ourselves with those names. All right. The next section, we'll talk about adding two vectors. A review for a lot of us. I'm going to give you two vectors. These happen to be in standard form. It's always a good place to start. So I want to add vector u to vector v. And when I do that, the way you add vectors is you take the first vector in your addition problem. So we're going to add u plus v. To do that, you're going to leave u in standard form, and you're going to move v, because vectors are movable. So I'm going to pick up vector v, and I'm going to slide it so that its tail is at the head of vector u. So I'm going to pick this up and move it like that, and keeping the angle the same and the length the same. So do you see I haven't changed the slant or the angle, and I haven't changed the length. So I just moved this up to here. So it's no longer here, it's up here. So this is how you add two vectors. You go head to tail. The head is where the arrowhead exists. The tail is the side of the vector with no arrowhead. So we go head to tail. So we're going to always add head to tail. And once you line them up, head to tail, you go from the origin to the head of the last vector. And that is the vector sum u plus v, that dotted line right there. So that is how we add vectors. If we don't have a picture of the vectors, we have a vector u, and its x component is u1, its y component is u2. You can tell these are components because they're in the pointy parentheses. And here, say we have another vector, its components are v1, v2. So these components totally define the vectors. How would we add them with math instead of with a graph? All we have to do is add the x components, so the u1 plus the v1. That will give us our new component on the addition vector, comma. Let me move this comma so we can see it relates, and then the y component of the sum of the two vectors will be just adding the y components of the individual vectors. So that's how we add. And again, I'm not really showing you the math of a particular example, but the theory. So imagine vector u was 1, 2, and vector v was -1, 4. Then you should be able to come up with their sum, the new x component, the new y component, by following that formula. All right, there's just a few other odds and ends left. Suppose we have a scalar number. That's just a number, k, and I am going to conduct scalar multiplication. Say k, I can think of it as a 3. That's what I mean by a scalar. So suppose I want to take k and multiply it times a vector like u. So it would look like this. We're going to take each of the components, u1 comma u2, and actually multiply them each by k. That's indicated with this formula. So the scalar k times a vector u is going to look like this. K, here's written in component form. And you would simply distribute the k first to the u1 and then to the k. Let me write my k's all the same. K goes to u1 and then k is multiplied to u2. All right. So that's how you will conduct scalar multiplication. So I might give you a vector. Say my vector is w, and the vector is -2, 3 in its component form, and I want to know what 3 times w is. So you should be able to follow this theory and tell me what the components are for 3w. They would be -6, 9. All right, but I'm not going to really do any of these. I'm going to let you figure them out. All right, let's talk about the negative of a vector. So if you have a vector v sitting there, I was wondering what negative v would look like. It turns out that negative v on a graph will be taking the arrowhead from this side and putting it on this side. So it completely alters the direction of the vector. So this is now, it's no longer v, it's negative v. So any vector, when you are asked to find its negative, reverse the arrowhead and you will be looking at the negative of that vector. What about, in theory, if you had vector v and its x component is v1, its y component is v2, if I want negative v, it will simply take the negative of the x component and the negative of the y component. Make sense? All right. All right, the next thing that I want to talk about is drawing u minus v on a graph. And again, this should look familiar for many of us. Suppose I take vector u and subtract vector v. So I've drawn an example of u and an example of v. So I'm going to think of u minus v as I'm going to take, and first of all, before I start, I'm going to put them in standard position. So I'm going to move this vector. I love to move vectors around. And I'm going to put it right there. And I'm going to take vector u and move it around and put it right there. So I have them in standard position. And now I'm going to discuss u minus v. And I'm going to do it just like my addition, but I'm going to redefine this subtraction as an addition, u plus minus v. Because I know what minus v looks like. So I'm just going to add it head to tail, just like I did previously. So I'm going to start with vector v, and I'm going to reverse it. So here I took the head from vector v and put it on the tail, the previous tail. So I totally altered the direction of vector v. Now it's called minus v. And now I'm going to add those two just like I did before. I'm going to leave u by itself, unaltered, and I'm going to remove this one so that the tail is on the head of vector u. So when I move it over, I'm going to put it over here and it looks like this. And the resultant is drawn from the origin to the head of the second vector. And that is u minus v. Right there. All right. Mathematically, how can I talk about that? Let's see. So say I have v equals v1 comma v2, again the x component of the vector and the y component, and suppose that I have got vector u, let me just move this, vector u u1, comma, u2. So the x component and the y component. And if I want to do it mathematically with no picture or vectors to draw on a graph, I will do u minus v like this. I'll think of this as u plus a minus v. But then remember that my x components for the u vector are u1, comma, u2. So I just wrote this vector in component form, plus, and now the negative of vector v, which we discussed previously, is minus v1 minus v2. All right, to add these, I'm going to just take these vectors and add their x parts and add their y parts. So u1, adding the x components, I get u1 minus v1 as the new component, x component of the difference of the two vectors. And then this y component will be u2 minus v2. All right. Again, this is all theory, so when you get a chance and say vector v's components are 3, 4, and let's say vector u's components are minus 1, 2, would you be able to find vector u minus vector v just by watching the theory? Hopefully you'll be able to trace that and use that tomorrow. All right, we'll end with some properties of vectors. And in this discussion, the vectors are going to be named u, v, and w, while constants are going to be represented with a c and a d. The first property of vectors is that they are commutative. If you add u plus v, vector u plus v, it's going to be the same if you add v plus u. The second property is an associative property, where you have three vectors added together, but these parentheses means you add these two first, and then the third. You're going to get the same answer if you add the second and third first, and then add the second and third, and then add the first one. So the order of operations won't matter. In addition, association it's called. If you have a vector u and you add 0 to it, you get 0. You get the original vector again, unaltered. If you add a vector and it's negative, you get 0. If you have a constant times a vector, and you're going to multiply that by another constant, it's the same as multiplying the two constants first, and then times the vector. So it's another association property, associative property. Here, if you have two constants added together times a vector, you can distribute that vector to each constant. So we have the distributive property. And that works the other way. If you have two vectors added times a constant, you can distribute the constant to each vector. So another type of distribution. 1 times any vector is that vector. And 0 times any vector is 0. And last but not least, the magnitude of a constant times a vector. Remember, these two double lines means the magnitude or length. The length of a constant times a vector equals the absolute value of that constant times the magnitude of that vector. All right, so all vector quantities share these 10 properties. So there they are. All right, you'll be asked to put this theory to work in real life or real vector problems with real numbers tomorrow. So look over them and make sure that you watch the video and the video didn't just watch you, so that you can add specific meaning to these theories. So look them over again and again, and I'll see you in class. Bye.